Hello, welcome back to e-learning in Honors Precalculus. In a Part B video of 10.1 Probability Chapter, I plan to complete discussion of some more of the topics in Section 10.1. Again, since this video lesson exactly parallels the material from the chapter, you may prefer to read that either online or from the PDF captures available in our shared Google Drive. So let's begin with the concept of independent events. In probability, two events are independent if the occurrence or non-occurrence of one of them does not affect the probability of the other one occurring. So, good examples. I flip a coin. Whether I get a head or a tails on the coin is completely unaffected by whether I got a head or tail on the coin flip before it. If I roll a die, the fact that I get a 5 on one roll has absolutely no bearing whatsoever on how the second one comes up. Now, for contrast, consider the event that a card is a spade. So if I draw a card from a deck, um, the probability of it being a spade is, of course, 1/4. But if I don't put that card back, how it came out definitely impacts the next card. For instance, if the first card is a spade, the probability a second card would be a spade is only 12 out of the 51 remaining cards, since I've already drawn a spade. But if the first card is not a spade, then the second card has a 13 out of 51 chance of being a spade. So you can see that those two events are linked. They affect each other. They're not independent. If I know the probability of two events, I can calculate the probability that both will occur using the multiplication principle of probability. This is whether the two events are dependent or independent. The multiplication principle of probability says that if event A has probability P1 and event B has probability P2, under the assumption that A occurs, then the probability that both A and B occur is P1 times P2. For instance, suppose I'm interested in calculating the probability that I draw two spades from a deck of 52 cards. The probability that I will draw the first spade is 13 out of 52, or 1/4. If the first one was a spade, the probability of the second spade will be 12 out of 51, which simplifies to 4 out of 17. So the probability of two spades is the product 1/4 times 4/17, or 1/17. Remember Sal and Val and the chocolates from the previous video? Previously, we calculated the probability of Val picking two of the four vanillas out of a total of 12 chocolates by dividing the number of ways you can choose two of four vanillas, or choose two, by the total number of ways you can choose two of 12 chocolates. 4 choose 2 over 12 choose 2 simplified to 1/11. I can use the multiplication principle of probability to calculate this a different way. The chance of Sal choosing the first chocolate to be vanilla is, of course, 4 out of the 12, because 4 of the 12 chocolates that are there are vanilla. When he chooses the second one, there are only 3 vanilla creams remaining of the 11 remaining chocolates. If I simplify this, it turns into 1/11 using the multiplication principle of probability. In numerically small groups of objects, like a deck of cards or a box of chocolates, the chance of a second one being affected by the first one is pretty significant. If I draw a queen as my first card, the chance of a second card being a queen is quite a bit reduced. However, with large populations, the probabilities do not change significantly, and we can treat them as their independent events. Consider the following problem involving blood types. So according to the American Red Cross, the distribution of blood types in the U.S. population is 45% are type O, 40% type A, 11% type B, and 4% type AB. I choose two people at random. What's the probability that both have type O? Technically, these are not independent events. As soon as I select the first type O, the population percentage of type O should theoretically drop a little bit because there's one less type O person to choose. But considering the population is very, very large, we treat these like independent events, and we just consider that the type O probability continues to be 45%. So the answer to part A is 0.45 times 0.45, which is 0.2025 or 20.25%. To answer B, let's consider the event being not type A, since the probability of type A is 40%, the probability of not A is 60%. So the probability of neither having type A means both have non-A, which is zero point 0.6 times zero point 0.6, or 0.36, or 36%. To calculate C, both have the same blood type, is really a combination of four different possibilities. They're either both type A, or both type O, or both type B, or both AB. You probably noticed I got A and O wrong in the beginning. So the first one we calculated as 0.2025. The second one is 0.16. The third is 0.0121. And the fourth is 0.00016. My mistake. The last one is 0.0016. Adding these up, we get 0.3762. So the probability of both having the same blood type is about 37.62%. This concludes part B of our Introduction to Probability, section 10.1. I will publish this, and then I will come back with more materials involving Venn diagrams and tree diagrams and conditional probability.